Here we are. Welcome to the physics video lecture. It is Psci 168, video lecture 32. And we're still talking about solar energy. We did a detour off into wind energy, and I hope you guys found lots of interesting pictures and some other information. This time we're back to solar energy, and this is the biggest question of all, namely, how powerful is the sun? What I'm going to show you is that with the concepts and understanding that we've already developed, we can actually put a number on the power of the sun in watts, and that will lead to some other interesting conclusions. As I unfold this, not everything was proved by us this semester because some of it needs a little more physics, but I'm going to point out everything that we need to know and what we did learn. So here goes. How powerful is the sun? Is the sun? Question mark. And the idea is the sun is over here shining. Maybe I'll give it some red color. It's radiating light in every direction. And we are over here. Now these relations are of course not accurate, but I'm going to put the numbers there in a moment. So one number we need is the distance from the sun to the earth. And we also need the mass of the sun. All right, mass of the sun, hence of the sun. We're going to need the mass of the sun, the distance to the sun, and we already know the solar constant, and that's going to come into play as well. So how many watts is the sun delivering if it were just a big giant light bulb? So as I put these things down here, I'll discuss a bit how we know them. So in fact, I had written down, I think, a chart of these numbers earlier in the semester, and I'll just remind us what type of quantities we had here. We had radius of Earth, we have radius of the moon, we had distance Earth to moon, and then we also had the distance Earth to the sun and the mass. And then we have the mass of the sun and some other ones there. So I'll just remind us, we had the radius of the Earth was R sub E 6.37 times 10 to the 6 meters. By bringing that up, I can remind us of how we figured that out. Basically, geometry, right? Geometry and geography. Take a trip north-south, measure some angles of the sun in the sky, and with geometric reasoning, we figure out the radius of the Earth. So for the moon and these distances, I will just say similar reasoning is used. It's more extended, but it's basically geometric reasoning that gets us these kind of astronomical quantities. So the distance from the sun to the earth that we need up there, so I'm using lowercase r for these distances and these uppercase r's for these radii. These things, of course, you can always look up, but let me go ahead and write down what we have there. The distance from the sun to the earth is approximately 1.5 times 10 to the 11 meters. These numbers become so huge, you definitely need your scientific notation. And now the mass of the sun is different. So for these here, let's just write geometric reasoning. Geometric reasoning and measurements. In fact, how about if I just write geometry? That's how we get these types of things. Sometimes you need a telescope, you got to make careful measurements, but it's down to geometry. Now the mass of the sun is different. That requires something else, and I'll describe it a little bit. So m sub sun, first of all, let's plug in what we have there. It's enormous. Roughly 2 times 10 to the 30. 2 times 10 to the 30 kilograms. So we're going to make use of that. So let me say a couple of words about how we discover the mass of the sun. We can't discover it by geometry. So to find the mass of celestial bodies, for example, as the sun, we need dynamics. Okay. We need Newtonian dynamics. The mass was always a dynamical quantity when we introduced it. And in this case, it turns out that if you know the distance to the sun and you know how long the orbit takes, you immediately know the mass. Same thing if we know the distance from the Earth to the moon and how long it takes for the moon to orbit the Earth, we know the mass of the Earth. So, for a central body that's being orbited, so here's the central body, say that's the sun, and that's the Earth. And there's again, distance sun to Earth. So for central body being orbited by a smaller one, period of a satellite orbit, which is t, along with the distance or the radius of the orbit, is enough for us to know what the mass is. Satellite orbit t and the radius of the orbit allow us to determine the mass. So that would be a deeper look into physics, but obviously it's a great chapter of it. I just want to mention to you how it's done. So let's make a note first. That's about the period. I'll just parenthesize the period and the radius of the orbit allow us to determine the mass. And that's how all these masses of the various bodies, you look them up in a book or you look them up online, you wonder, how did they find out the mass, say, of Jupiter? Okay. Well, Jupiter has a lot of moons orbiting it, and if you time that and measure these distances carefully, which is geometry, okay, then you can find the mass. So for that reason, we treat the distance to the sun as known and the mass of the sun as known in what follows here. We need both of them. Well, we need the mass for a different purpose, but we need the distance to the sun, and that's actually all we need now to determine the power of the sun. So let's talk first about the power of the sun. And we've set it up there. So power of the sun. And what I'm going to do is just set up that picture a little bit differently. So again, we have, I'll make it a little smaller. We've got our radiating sun in the middle. Our Earth orbits the sun. again, that picture is not to scale. In fact, I'm going to put it even closer here. Okay, so there's the Earth, and here's the Sun. Now, what we're going to make use of is the fact that we know the solar constant. So the solar constant, remember that was just the power of the sunlight here at our Earth. I was equal to 1,340 watts per square meter. So out here at Earth, we set up those 1 meter square solar panel, and we have 1,340 watts. So to get the entire power of the sun, we imagine encasing the sun in a sphere of radius distance of sun to Earth. And then radiation is going not just to that 1 meter squared there, but through the entire surface. Okay. So we've got the solar constant here. We have the surface area of a sphere. Surface area of a sphere. And I'll just call that A 4 pi radius squared. So it's that easy to get the power. We're just going to multiply the solar constant times the surface area in square meters, and the square meters are going to cancel, and we're just going to end up with watts. And remember that solar constant, that's practically a backyard experiment. The distance to the sun, of course, is a little more involved, but those two quantities alone will give us the power that we're looking for. So I'll write these things down. You guys should get your calculators out and make sure this is all working. So let's just put this in words. Power, well, let's write it out. P is going to be the solar constant I, which again is in watts per square meter, times this enormous number of square meters, 4 pi distance from the sun to the Earth squared. Okay. So power P equals I times A, solar constant times area. I'll write it out, I times area. And we just have to plug these in now and see what happens. That's all of the power. It's just going in every direction. So that's why it's just going through that entire surface there. 1340 at the location of Earth, which is where we are. Good, so what do we have here? 1,340, so 1.34 times 10 to the third watts per meter squared. Then we've got 4 pi, that's roughly 12, a little more, I'll just write 12. 4 times 3 point something, 12, 12 and a half. 12 is good, so 1.2 times 10 to the 1. Okay. And now this distance to the sun to Earth squared, we have 1.5 times 10 to the 11. 10 to the 11 meters quantity squared. So let's see if we can do this. So we have 1.34. And then I'm gonna pick up the powers of 10 later. And then we've got the 1.2. The 1.5 squared is 2.25. And then we'll have times 10 to the 3 plus 1 plus 11 times 2, right? It's squared plus 22. 22, 3, 4, 5, 6. This will be watts. And we can do a quick estimate of this, I think. So 1.3 times 1.2 to 1.5, 2.25 times 1.5, about 3.6 or something. You guys multiply it out. I have here 3.8 in my notes. Let's just say approximately 3.8 times 10 to the 26 watts. P sub sun. Okay, that's a pretty amazing calculation right there. So that's not all of it though, so that's just a big number. And of course, Earth is just capturing a tiny, tiny fraction of that. We're so far away, we're really just like a little dot on this. And this was an enormous amount of square meters right here. Okay? But that's the total power radiated by the sun. Power radiated by the sun. By the sun. Okay, so we did not need the mass, but the next discussion point is going to require knowing the mass of the sun. Okay. At this point, it's such a big number, obviously we need the scientific notation, and it's hard to put into relation to anything. It's just an enormous number. However, we are going to put it into relation. Because the question now comes up, sun is radiating that much power, can it go on forever? If the sun were made of some kind of fuel and that fuel is burning, and it's burning at a rate of 10 to the 26 watts, so 10 to 26 joules per second, how many seconds can this thing burn before it runs out of fuel? So that's going to be our next question. And I'll go ahead and leave this up here, and we'll have to make use of the mass of the sun, because our argument is going to be, well, suppose the sun is completely made of fuel. Well, we know how much energy fuel has, gasoline, you name it, coal, and that's what we'll use. We'll get the total energy, and then we'll be able to compare it to this power with some interesting consequences. So that's our next step. We have this. I hope this is clear what was going on, and that's how we got the number there. Basically, we measured this on Earth, okay, the solar constant. Good. Let us move on to this next idea. And this is where we come into some unknowns, because when this was first done in the 19th century, nobody knew what the sun is burning. Okay? It's bright, it's warm. We now know, we knew its power at that point, but we didn't know what type of fuel is being consumed there. So our next question, let's go ahead and say, how long will the sun continue to burn? Let's formulate this. Let's put it this way. If the sun is burning fuel, how long until it runs out of fuel? Until it runs out. You don't expect something to be able to just burn forever, right? The fuel eventually runs out. So that's our question. And the first thing we need is the energy of the sun in joules, if it's burning fuel. So what we'll do is we'll take the joules per kilogram of fuel and then we'll multiply it by 10 to the 30 kilograms. Okay. So for fuel, we have, let me see what's the way I'm going to start on this, what order. Yeah, I'm going to do this energy density. So for fuel, we're going to write an energy density in joules per kilogram, and then we'll just multiply it through by kilograms. So we start this way. We have we're going to write, for fuel, we're going to write 10 calories per gram. Okay, so it's like gasoline or something. So 10 calories per gram, we're going to multiply that by 1,000 grams per kilogram. But then we have to do the calories here, and we'll just do 4,000, we'll simplify it, joules per calorie, and then the calories cancel, the grams have canceled, and we can just multiply that out. 4 times 10 to the 1, 2, 3, 4, 5, 6, 7. So 4 times 10 to the 7 joules per kilogram. That's what we're going to take for the energy density. And you know, 4 and 2 is a good number. I could even round it up to 5 if I wanted to. So I'm going to round it up to 5. Approximately 5 times 10 to the 7 joules per kilogram. You know, we could have some slightly better fuel, okay? Although that's a good number. Now, this next point, so we have this number 2. Energy, I'll use capital W for work. The energy is going to be equal to 5 times 10 to the 7 joules kilogram times 2 times 10 to the 30 kilograms. 2 times 10 to the 30 kilograms. And what is that? That's the energy in the sun if it were made of fuel, if it were just burning fuel. So you see, that's why I chose that number there. So 5 times 2 is 10, that's 1 more power of 10. So I can just add them up. 30 plus 7 plus 1 is 8. So that gives me 10 to the 38 joules. So that's the energy in the sun if it were made up of fuel. Let's go ahead and make sure we hold on to that. So we have a power, 10 to the 26 watts, and we have a maximum energy if the sun were made of fuel. And now if we divide those two numbers, we can get the number of seconds of how long it will burn. So by the way, leave some room in your notes. You guys should take all of these things and make sure you multiply them out. Make sure I'm not making a mistake. But I'll give you, see right here where I've rounded up. I rounded down there a bit, rounded up. This is all very good ballpark estimate. So finally, in this calculation, how long until it runs out? That's the question we're going to answer here. Now I can erase all of this. We need these two numbers, so we'll hold on to this. I'll erase this right here. Now remember our definition of power. So finally, let's go ahead and write this out. We have power is energy per time, because remember the units. Watts equals joules per second, right? So we can just solve this equation for time. I think we've done this before as well. So the time is going to be the energy divided by the power. And because we're using our consistent units, joules, seconds, watts, the number that comes out here will be seconds. So let's see what we get here. We have the energy as 10 to the 38 joules divided by 3.8 times 10 to the 26 watts. And remember, the watts are joules per second. That's why the answer, you're going to flip that there. The answer is going to be, joules are going to cancel, seconds going to appear in the numerator. So here I don't have a calculator, and I use different numbers this time, but I'm going to consult my old numbers here anyway. I'm getting, so use your calculators on this. Actually, I'll write it out and then we'll see what if it makes sense. 2.6 times 10 to the 11 seconds. 2.6 times 10 to the 11 seconds. Right, that's again one of those large numbers, we can't really gauge it right now. But actually, 38 minus 26 is 12, and 10 over 3.8, or 1 over 3.8 is less than 1. That does it. So 2.6 times 10 to the 11. Go ahead and plug that into your calculator, see what you get. Should be close. And then we want to convert this to years. So this is seconds, and we're just going to divide by 365 days times 24 hours times 3,600 seconds, and this is all per year. So this is the way to, so we can hold this number in terms of seconds. If we do this division here, seconds cancel, the year comes up into the numerator, and I'm getting something like 8,200. I'll write approximately 8,200 years. Okay, so this now is an amazing result. So this was done sometime towards the end of the 19th century. So just a bit over 120, 130, 140. Could have been more than 150 years ago. But at that point in time, 100 some years ago, it was clear that the Earth had to be much, much older than 8,200 years. A whole lot, much, much older, because of processes in geology and biology. So yeah, the physicists were in an interesting position. Their theory had just come up with 8,200 years, which is simply not enough. And what is the resolution to that problem? Well, the resolution is that we said if the sun burns fuel, the sun is not burning our ordinary fuels with, 10 to the 7 joules per kilogram. you could take this as the beginning of the understanding there had to be other energy processes in nature, and in fact the sun burns nuclear fuel, nuclear reactions, instead of a chemical reaction. And a nuclear reaction has up to 1,000,000 times the energy output compared to just chemistry. Burning fuel, fuel and oxygen, that's chemistry. So, and involves the electron shells, but if you're involving the nuclei, you can get up to 1,000,000 times more energy, and therefore the Earth or the sun can be, on the order of 1,000,000 or definitely hundreds of thousands of times as old as 10,000 years. So yeah, that's what we get out of this really basic idea. We got the energy in the sun based on if we're burning fuel. The power, this is literally a true statement about the power of the sun. Okay. If you measure the solar constant on Earth, this is just a geometrical factor and you actually get the power of the sun. So we could say we're part way to the discovery of nuclear processes. Namely, at this point we don't know what the sun is burning, and it's going to be later developments that tell us about the nucleus of the atom. So I'm going to leave it at that. I'll put a couple words here commenting on this 8,200. And you guys just go ahead and control these calculations with the calculator, make sure we didn't have any mistakes slip in here. So there's a star. So note this age is much too young, too small for Earth, because so much has happened on Earth, so many geological, biological processes that, that take millions of years. Okay. So it's much too small. The sun does not burn fuel as in a chemical reaction. Chemical reaction, but rather, or I'll just leave that there. What then remains to be discovered is nuclear reactions. Involving the atomic nucleus yield, up to 1,000,000 times as much energy. Much more energy and all right, on the order of 10 to the 6 times as much. So there you have it. That's what I wanted to finish our discussion of solar energy with, power of the sun, and that there are other things, and in fact nuclear energy is a source of energy here on Earth as well. But those energy sources, which we're not really going to get into, they are hooked up to ordinary heat engines. Okay, so the nuclear reactions are used as a source of heat, and then we hook them up to heat engines, which we have studied. So good, we'll leave it at that, and see you guys next time.